Hello everyone, welcome to my YouTube channel. It's me Javindra Paudel. Today I am going to evaluate the modal time period of the structure by the empirical formula as given in the code NVC 1052020 as well as by the Rayleigh method and compare the obtained time period from these two methods with the values obtained in the ETABS. So in my previous video, one of my previous video, I have already developed the model and evaluated the story stiffness or stiffness of the building and compare that stiffness manual calculation with the value obtained from the ETABS. So today I will continue from that part, or I will take that model which I already used for the stiffness evaluation. So this is the model I used for my previous video, and I will continue from this model and evaluate the time period of the structure by both method and compare the time period with this value obtained in ETABS. So basically, while doing any analysis, either linear or non-linear, it's very important to know the model, this built-up model or constructed model is correct or not. It is necessary to check the model with some parameter called model time period frequency and the model mass participation factor, and these things can be found from the model analysis. Generally, the model time period of the structure can be determined manually with the two methods as prescribed in the code I have already mentioned here. The first one is the empirical formula, and the next is the Rayleigh method. So if we look into the code for the empirical formula and Rayleigh method, here this is the code class for the calculation of model time period. The first one is Rayleigh and another one is empirical. And if you go into the Rayleigh method, the fundamental translation period in the direction under consideration, either it's mode 1 or it's mode 2 or XY mode 3 XY direction, the time period can be evaluated as t equals to 2 pi under root summation I equals to 1 to n wi square of divided by summation of Fi di into acceleration due to gravity, where di is the elastic horizontal displacement of the structure at its level, Fy is the lateral force acting at its level or at each story level, g is the acceleration due to gravity, and I is the level or story under consideration, n is the number of level of the structure. It means if we have a 13-story structure, the value of n is 1 to 13, and Wi is the seismic weight of the structure at its story level. So from this formula, the time period from the Rayleigh method can be evaluated. As we can see clearly here in the formula, the Rayleigh method depends on the dynamic properties of the structure, and it is widely recognized as a method of predicting the fundamental period of vibration of the structure. This method also determines the model shape and can be used to determine the second and third natural period as well as the mode shape. Besides this formula, this method, another one is the empirical equation that has been mentioned here in the code. And the empirical formula have to be, the model time period obtained by the empirical formula had to be increased by a factor of 1.25 in Nephe's code to account for the low period values, but not mentioning why to amplify this time period in our code. So if we go into the formula for the evaluation of time period by empirical formula, then t equals to kt as form 3/4, where kt is the constant and its value is different for different structural system. For example, 0.075 for moment resisting concrete frame, and similarly 0.05 for all other structural system. Means it includes the structural system with dual systems, shear wall, including the shear wall or coupling beam in the structure, and 0.085 for steel frame and 0.075 for eccentrically braced steel frame, where h is the height of the building from the ground level to top of the building, and this value shall be increased by a factor of 1.25, which will evaluate the time period by this method and as well as the Rayleigh method, and compare this value with the ETABS, and we'll see clearly what is the difference of the model time period in manual calculation and in finite element software. So, at first, let me go to the NBC 1052020 for the manual calculation by empirical formula. Here I have developed the Excel sheet with the inclusion of the provisions in the codes in the NBC 1052020. And let me start from the beginning. So I choose the location of the structure to be in Kathmandu. Why this is important? Let me describe. If we choose the location of the structure in different parts of Nepal, like here, the seismic zone factor is different for different areas or different selected cities and municipalities as prescribed in the code. So here the seismic zone factor for Kathmandu is 0.35. Here I choose Kathmandu. So if I choose Khalanga, it's 0.3. For now, let me choose Kathmandu. Kathmandu, yes. And the seismic importance factor is also prescribed given in the code. Structure here, the seismic class and importance factor are categorized into three importance classes depending upon the type of the structure, depend upon the consequences of the loss of function. The important class are characterized by the importance factor I. There are three categories of importance factor. The first one is I equals to 1. The second one is I equals to 1.25, and the third option is 1.5. For I equals to 1, it's not a special type of structure. For only for ordinary structure. For example, let's say a residential building. We can incorporate the value of I as 1. And for the buildings like school, college, cinema, assembly buildings, such as shopping malls, convention halls, templates, monumental structure, police station, etc., the value of I is 1.25. If this structure are to be used as a shelter in the case of earthquake or any disaster, these values also have to increase to 1.5. It is clearly mentioned here. And the rest is the hospital, fire station, the police headquarters, power station, etc. We have to incorporate the value of I as 1.5. For now, let me choose I equals to 1.25. It means I treat this building model as shopping center, and the height of the building is, let me go to the ETABS model. The height of the building is, I think it's 39 meters. It's 41.6 meters. 41.6 meter. And in Kathmandu, the type of the soil should be considered as soil type D. I'll show here in the code. Okay. Soil type D is for very soft soil site, which comprise of cohesive soil more than 10 meter depth and under soil strength less than 12.5 kPa and SPT values are less than 4. Such site have a typically low amplitude natural period greater than 1 second, and site located inside Kathmandu Valley are obtained from the table 4.4 are considered as type D soil. Okay, we consider the Kathmandu as type D. Here, if we see the curve, this one is the spectral shift factor for type D soil for response spectrum analysis, and if we look into equivalent static method, this one is the type D soil response spectra. So let me turn into the calculation of fundamental time period of the structure. We already saw that the time period of the structure is given by the formula as empirical formula here. This one is the formula, and the structure consists of dual frame system. So I consider it as sorry, all other structural system. Then for all other structural system, the value of kt is 0.05, and the approximate fundamental time period of the structure with the formula kt into h for 3 by 4 3 by 4 is 0.819 second. And if we amplify this formula by a factor of 1.25 as prescribed in the code, the time period obtained in the by the empirical formula is 1.024 second. So after this, let me turn into another section of the time period evaluation. So for Kathmandu, if we consider the soil type T and Kathmandu, these are the equivalent soil parameter for the curve, which we can see here in the table. Yeah, in the table for soil type D, if we choose the equivalent static analysis, TA is 0. Here the TA is 0. And if we choose the response spectrum analysis, the TA is 0.5, the TC is 2, and the alpha factor is 2.25, and the K factor is 0.08. So here we got the spectral highest peak spectral factor of 2.25. As we see here, this is the peak plateau, horizontal plateau for 2.25, and elastic site spectra for horizontal loading CT equals to CST into Z into I. CST is 2.25, Z is 0.35 for Kathmandu, and I is 1.25 as we mentioned here in this Excel sheet. The elastic site spectra for horizontal loading is given by the formula in the class 4.1. Here 4.1.1 CST into Z into I, and we got 0.984, and elastic site spectra for serviceability limit state is 0.2 into CT. It means 0.19875, and the elastic site spectra for vertical loading is 2 by third of Z. It's mentioned here. Yeah, the elastic site spectra for vertical loading shall be given by 2 by third into Z. It means 0.233 is a multiplication of 2 by third of 0.35. So after this, let me go to the ductility and overstrength factor. So for this factor, let me go to table 5.2. Here are the ductility and overstrength factor for ultimate limit state and serviceability limit state. So I considered my structure as dual structural systems, which is composed of moment frame and coupled shear wall with a coupling beam. So I put the values of ductility factor and overstrength factor as the value prescribed in 19 serial number 19 3.5 and 1.4. It means RB equals to 3.5, overstrength factor is 1.4, and the overstrength factor for serviceability limit state is 1.2. So the horizontal Wessier coefficient at ultimate limit state CDT1 equals to CT by R, which means the R is the combination of R mu into omega mu. So CT by R is, we got 20.1%, 0.201 for ultimate limit state and 0.161 for serviceability limit state. So if we go to our model, we need to insert the Wessier coefficient of 0.201 and 0.164 for the ultimate limit state and serviceability limit state. So if we look into the value of Wessier, first of all we need to calculate the seismic weight of the structure. The seismic weight of the structure I will calculate from the model and copy paste it here. So let me go to the model for the evaluation for the model analysis. But before that, we need to calculate the exponent related factor k to time period. So as prescribed in the code, the value of k is an exponent related to structural period, which is as follows. For a structure having time period less than 5 seconds, value of k is 1, and the structure having time period less than 2.5 seconds, its value is 2. And for the structure having modal time period between 0.5 second and 2.5 second, the value of k shall be determined by using the linear interpolation of the two values. So, for example, our building is 13 story. Its time period falls between 0.5 and 2.5. Let me go to the empirical equation for the time period. So we got the time period of 1.024 second, and the interpolation, after the interpolation, the value of k is 1.262. So these values shall be applied to the model with the Bessier coefficient. So let me go to the ETABS model. So here, this is the ETABS model. First of all, let me go to the load pattern. It is EQX for NBC ultimate limit state. Let me modify it. Here, the Bessier coefficient is 0.201 and the building height exponent factor is 1.262 and eccentricity ratio for all diaphragm is 0.1 as prescribed in the code. So let me click OK. Again, I choose 0.164. 0.164. Okay, then for y-axis also same value 0.201 for ultimate limit state and serviceability limit state is 0.164. 0.164. The story top is 13 and bottom story is base, and the eccentricity ratio for all diaphragm is 0.1. So let me click OK. If we turn into the seismic weight of the structure, the seismic weight 8 is labeled Wy, shall be taken as the sum of the dead load and the factor live load between the mid height of adjacent stories. So in NVC 1052023, the factor for the live load is 0.3, and for storage such as water tank, etc., is or other warehouse storage is 0.6, and for the roof load the factor is 0. So we need to calculate the seismic weight of the structure, which is the sum of dead load plus 0.3 of live load or 0.6 of storage load. So the dead load and live loads shall be determined from this model. Let me run this model. So let me calculate the seismic weight of the structure from this model. I have already run the model. So let me go to display, show table, and structure output. Here you can see the model properties also, the time period of the structure as well as frequencies and the base reaction. Okay. Here the dead load of the structure is 51952, live load is 1681, and STL I have applied the one load as STL load in terms of area load for the simplicity now is 18252 kilonewton. Here another combination I have made in load combination, the seismic weight of the structure is 73708, which is same as dead load plus 0.3 live load. So let me go to seismic weight. If we make the seismic weight combination like this, dead load plus 0.3 live load, which is given by our code here, then we got the same value. So it is easier and it certain the time of calculation of the seismic weight. So we check the value by both ways. So again, let me go to the tables. Let me check here. The dead load plus live load plus STL is these values. I copy these values here somewhere here. Then dead load plus 0.3 live load equals to these two are the dead load equals to these two, the first one and the last one are the dead load plus 0.3 into live load. So now we don't have any storage load. So it's 73708 and here directly we got 73708.542 from making the combination of dead load plus live load, which is faster. So let me go to the Excel sheet. Here it's the value for the dead load is 73708 and the horizontal base here we got from the Excel sheet is for ultimate state is 14807.52 kilonewton and SLS state is 12092. So if we check the base here from the model, so let me go to story response plot. Here go to story share. We have to look the story maximum story share at the base, and let me go to EQX ULS. It is 14748, and if we go to SLS, it's 12033. It means 14807 and 12092. It's almost same. The value of base here is almost same for both x-axis and y-axis. So this can be, the model can be checked either it's correct or not by this way also. So we have already calculated the time related exponent factor of 1.262, and after that let me go to the story force. So the particular distribution of seismic force F Fy is calculated by this formula: Wi into Hik divided by Wi Hik summation into the horizontal seismic base shear into B. Let me check the story level mass in ETABS. So here, let me go to table, go to other definition, mass data, and mass summary by story and mass summary by diaphragm. Let me click OK. Then these are the mass. Okay, these are the mass. 8 is story level. I go to ETABS. These are the values obtained from the ETABS. Then this unit is in kg. So I have to convert the seismic weight in kilonewton. This multiplied by g value to convert into Newton divided by 1000 to convert into kilonewton. Okay, so do all this for all story. Then we got the seismic base here. The sum of story masses is 73399. It means it should be equal to the obtained base here 73708. 73708. It's near about that value. So after inputting this value here, then we got the ultimate limit state force at its story level due to the lateral loading or seismic loading. So here the formula for the force is Wi into Hi power k divided by summation Wi Hik into seismic base shear. Here Wi Hik multiplied this value divided by this value into the base year obtained in this set. So these are the force, story-wise force, and after this calculation of force, we need to go for the time period calculation by Rayleigh method because we need this force in calculation of time period. So these values are the proportion of the lateral force. Then for the time period calculation, the formula is the fundamental translation period in direction under the consideration shall be calculated as 2 pi into under root summation I equals to 1 to n means the story level, wi di square divided by acceleration due to gravity, and Fy into di, where d is the elastic horizontal displacement at the level I, Fi is the lateral force acting at each story, g is the acceleration due to gravity, I the level under consideration, n number of stories, it means there are 13 stories in our model, n equals to 1 to 13, and wi equals to seismic weight at each level I. So here wi is already mentioned here, which is same value as this calculation, and we have to go for displacement h each story in the software. So this theory clearly indicates that Rayleigh method implies utilize the dynamic property of the material. So let me go to maximum story displacement, go for ultimate limit state for x direction. Then these are the story displacement. So let me copy this here, paste here. Please reminded that these are in unit. We have to convert into meter. So di square, and this is the force which is mentioned here, same as there. Yeah, and wi di square is wi. It is in kilonewton. Di square means square. This di into square. So this value have to be converted in meter square. So multiplied by 10 to the power minus 6. Then we get Fi di. So we get wi di square and Fi di also. So from this table, we got all the value that is required for the calculation of time period. So the fundamental time period T1 equals to 2 pi under root summation of WIDI square by summation of FIDI into acceleration due to gravity. And after this, we got the fundamental time period for acceleration or mode 1 is 0.984 second. Let me go to ETABS to compare the time period of the structure. Here, let me go to the model time period first time period. Let me click OK. Then we get 0.983 second, which is exactly same as the value obtained from Rayleigh method. Similarly, if we calculate for y-axis, we have to insert the displacement along the y-axis. So let me insert the displacement along the y-axis. These are the displacement. Let me copy here. Okay. Then we got the fundamental time period of 0.818 second in y direction mode. So in other mode, let me check the time period of the structure. This is 0.879. It means the building is in torsion. So for y direction, let me go to another mode. I mean mode 3. The time period is 0.815, which is exactly same as the time period obtained from the Rayleigh method when rounding up 2 digits. So the time period we got from the empirical formula is 1.024 second, whereas from Rayleigh method is 0.984 second, which is exactly same as the time period obtained from the finite element method. So while doing manual calculation, we have to incorporate the less time period of the structure to have little conservative value of the seismic force or seismic behavior of the structure. So these values are the accurate value. The value obtained from the Rayleigh methods are the accurate values uh, or near about values as compared to the empirical method. So in the next video, we'll proceed for other linear static analysis and response spectrum analysis, as well as time history analysis and so on, and design the structure. So until that, keep watching my videos. Don't forget to like, share, comment, and subscribe my YouTube channel. Thank you.